Thank you, quantum mechanics. Quantum mechanics is one of the most successful ideas human beings have ever created. It powers our phones, it powers our computers, it explains why matter exists at all. And yet, after more than 100 years, we still don't fully understand what it's really telling us about reality. So today, this isn't an explanation video. This is a thank you. A thank you to the theory that shattered certainty and replaced it with wonder. At the end of the 19th century, physicists felt confident. They believed the universe was almost figured out. Matter was made of particles. Forces were carried by fields. Gravity pulled, electricity pushed, magnetism curved. Find all the particles, list all the forces, write the equations, and physics would be complete. But the universe had other plans. When scientists first imagined the atom, it looked familiar. A dense nucleus in the center, electrons orbiting around it like planets around a star. It felt comforting, intuitive, human, and completely wrong, because an electron is an electric charge, and a moving electric charge must radiate energy, which means that electron should lose energy, spiral inward, and crash into the nucleus. According to classical physics, every atom in the universe should collapse almost instantly. Your body should not exist. This chair should not exist. The world should not exist. And yet, here we are. Quantum mechanics didn't arrive as a dramatic announcement. It arrived reluctantly, piece by piece, through failure. Experiments kept disagreeing with classical predictions. Light behaved like particles. Particles behaved like waves. Nothing stayed in its category. Then came the wave equation. Schrödinger's equation. It worked amazingly well. But it introduced a new question, one that physics had never been forced to ask before. What does this equation actually describe? At first, people hoped the wave equation described something physical, a smeared-out electron, a real wave in space. But the math refused to cooperate. Then Max Born made a radical suggestion. The wave function doesn't describe what is. It describes what can happen. It's a map of probabilities, not ignorance, not lack of knowledge. Probability itself became part of reality. And with that idea, physics crossed a line it could never uncross. Here's where things get uncomfortable. In classical physics, measurement is passive. You observe the world without changing it. In quantum mechanics, measurement is different. When you measure a system, the system changes instantly, fundamentally. And the theory itself depends on this idea. But it never clearly tells us what a measurement actually is. Is it a human observer, a machine, an interaction with the environment? Quantum mechanics gives perfect predictions, while refusing to define one of its most important concepts. This is what we call the measurement problem, and it's still with us. Then reality becomes even stranger. Sometimes two particles don't have separate stories. They share one description, one wave function, one probability structure. Measure one, and what you can predict about the other changes instantly. Not because information traveled faster than light, but because they were never fully independent to begin with. Entanglement teaches us something deeply unsettling. At the most fundamental level, reality is not made of isolated pieces. And then came the realization that quietly ended the wave-particle debate forever. Particles are not fundamental. Fields are. The electron is not a tiny dot moving through space. It's a vibration in an electron field. Light is not a stream of pellets. It's an excitation of the electromagnetic field. Everything is fields. Particles are how those fields appear when we interact with them. The universe is not made of objects. It's made of activity. From this framework, something extraordinary emerged. The standard model of particle physics, a structure so precise that it predicts experimental results to astonishing accuracy. And yet, it's messy, uneven, filled with strange patterns and unexplained values. It works, but it doesn't feel final. Because when we look beyond the lab, the universe still hides things from us. Dark matter, black holes, the first moments after the Big Bang, and above all, gravity. We know how to describe gravity classically. We know how to describe the quantum world. But when gravity becomes extreme, quantum mechanics and space-time stop agreeing. And today, we don't know how to merge them. Not because we're careless, not because we're lazy, but because the universe is deeper than our intuition. Scene 10. Gratitude, not closure. So this is not a story about answers. It's a story about humility. So this is not a story about answers. It's a story about humility. Quantum mechanics taught us that reality doesn't owe us clarity. That intuition is optional. That certainty is fragile. And yet, it works better than anything we've ever built. Thank you to the scientists who followed confusion instead of comfort. Thank you to the equations that worked even when we didn't understand them. Thank you to the universe for being strange enough to stay interesting. Quantum mechanics didn't give us certainty. It gave us something better. A reminder that we are still learning, and that the deepest truths of reality are still waiting.